So hi, thanks for joining this talk. So I'm Valérie Allier, I'm Video Solution Director at Interdigital. Oops, sorry. Let me just be at a good position. So Interdigital is a global research and innovation company specialized in wireless and video technologies. We are this year at AWE showcasing some demonstration and technologies. That's strange, it does not change. In my PC is okay. And this one not. Let me check. I have made a bad. Yeah, let me see. That's perhaps my point. Let me check. Yeah, it's me. Oh, sorry. So we are here this year at AWE showcasing some technologies. We are currently developing jointly with Philips, where we have a research collaboration with Philips in order to collaborate to enable and deploy video-based immersive codecs for XR opportunities. So our goal is to jointly show the capabilities of video-based codecs to enhance XR experiences, thanks to when we bring this video, volumetric video, inside the experiences. And we are open to engage with the industry ecosystem to deploy such solutions. So we think that real volumetric video will transform telelearning application and create a path to Copresence experiences. So if we look at the telelearning and Copresence, we all experienced that with this COVID pandemic, we had a rapid shift to different educational models. And we also realized the lack of tools to really get more immersed, and we have remote working, remote collaboration, remote telelearning. At the beginning, we were all happy with Teams and 2D videos. Now we are really suffering with these flat videos. We see also presence as a primary and strongest use case for XR enterprise and at consumer levels. That's really what people try to tend to have. And we are just at the example of the previous talk. So what we have seen also in telelearning application is like in education, online training, instructions, is that where you bring this XR viewing, you get a greater level of engagement. We had also this talk, a panel on creativity in XR, saying that yes, when you go to 3D with volumetric information, people feel more engaged, get more memories of what they are seeing. So it's really bringing more value, more engagements, and more training results. And for that, we think that video-based volumetric media will bring a more natural and realistic experience to XR. So if we look at the technology roadmap, we think that the core video interactive media compression assets that we have been since years can build a roadmap from 2D video that we have today, streaming courses, towards a full co-working environment. So that's, if we look at offline, we start with offline content. Today, telelearning, you just go on the platform and you get access to 2D videos. We can imagine that we will get access to immersive videos, and this is what we are showcasing here at AWE. And then we will go to live. You have the live telelearning with live 2D streaming, and we will go to live immersive streaming to bring, again, more immersiveness. And that's the goal then, to have this co-working with dual link exchange of live content. And the same also with the way you interact with this telelearning environment. Today, it's let's say a platform where you can access to different video streams and you just consume those video streams independently. We can imagine that we can then try to synchronize them, bring some haptics and synchronization between the streams. And then the goal is to have that full 3D learning environments, a 3D space, an environment space where you have a global scene and scene compositing, where you can access to all those single streams. So at the heart of that, we think that we have a volumetric video, which are the heart of this telelearning application. So we think that it's representing the next generation of content, and we create more immersive experience. In fact, with volumetric video, you get more immersed into the content because you bring to the user the sensation of depth and parallax. So this is things that you can experiment. For here, for instance, we are just watching to a scene here. And I think that with the movements that we are showing to you, you feel the sense of depth. You feel the sense of parallax. You see, in fact, characters behind. And you also see here on the right, one single character. When you put that into a context, what you see here is that on the right side, you have this single character, in fact, which has been put on an AR application. And once you have a real person on an AR application, you really need this content to be really volumetric, because you have to cope with the external environment, which is 3D. And on the left, what you have with the scene, in fact, the scene you just seen before was not a video. It was just one frame of a volumetric video. And inside each frame, the user can get access to all the details of this frame. And that's the things that you really bring this sensation of depth inside the volumetric content. So volumetric content is a video in which the user point of view can be dynamically updated. And with video-based compression schemes and streaming content, the user point of view is directly provided on the device, directly provided with the video player. And for real immersive 6DoF experience with different viewing space based on the context and the capture system, we can see different type of content. We can see, as we have seen with the soccer guy, the viewer relatively close to the objects. And he can look at it from all the sides. This is what we call point cloud. You know very well point cloud. And we have a specific compression scheme called video-based point cloud compression. And the other part is that the viewer can be relatively distant and has an overview with larger field of view. It can get access to the large volumetric scene. The full scene is volumetric, is what we have seen just before. And for that, we have another compression format, which is MPEG Immersive Video. So one of the challenges of this volumetric media is that for dense point cloud or multi-view plus depth content, you have a huge amount of data that you want to deliver. And with MPEG, the objective of the MPEG V3C standards is to bring an efficient way to stream and deliver this type of content. So for that, we have a global framework called V3C, Visual Volumetric Video-based Coding. And inside that, you have different specific codecs based on the input data. So for point cloud, it's V-PCC, which is an existing standard. And for multi-view plus depth, you have the MIV. And you have associated standards related to the system support for the streaming, and later to scene description. And as you see here, we will have later also dynamic mesh compression scheme. So it's really to provide the industry with tools for efficient streaming and rendering of content. So with video-based point cloud. So we all know here the point cloud, what is a dynamic point cloud. So what's the input stream here is really a dense point cloud. And in order to stream this content, we use, again, video-based solution, is that the initial uncompressed point cloud is projected in 2D views. And we create 2D patches, and all these patches are packed so that we have 3 video streams. We have a geometry stream, a texture stream, and an occupancy map stream, which is really specific to be able to reconstruct the point cloud at the end. So finally, we will have 3 video streams, and we will use video techniques, compression techniques, to deliver those streams with HEVC or VVC, for instance. And doing that on the receiver side, we will receive all these patches, and we will be able to reconstruct all this information and create back the point cloud information and the 3D model, in fact. That will be done on the player side, and we will be able to navigate into this 3D content. on the MPEG Immersive video side, the input format is different, is a multi-view plus depth information. So we have a rig of camera, and the rig can be different, and depending on the size of the rig, you will have more capacity to navigate into the content. But the rig is made of different views, texture information, and depth information. If you talk about CG content, the depth is generated by the rendering engine, so you have perfect depth. And if you have real content, then captures with a real camera rig, you will use photogrammetry, videogrammetry to create this depth information. You have also for MIV another format, which is multiplane images or multisphere images, which is commonly used also for volumetric scene. And here, in fact, we don't consider multi-views, but we consider on one scene multiple slice layers at different depths. So that's finally we encode the different layers with texture information and transparency. And this MPI content can be created from a multi-view plus depth information, or can be created today with some deep learning techniques starting from the multi-view only information without the depth. And again, it's a video-based encoder scheme. So that's at the inputs, you have the multi-view information with the texture and the geometry. And when it's encoded, we create the central view and an atlas with all patches, which provides to the central view, the main view, all the information about occlusions that you can recover thanks to the multi-view acquisition. And then you provide this streaming, the V3C stream, and on the decoder side, you are able to synthesize the user position and the virtual view for the user inside a viewing space. On MIV, the viewing space on any volumetric video, the viewing space is dependent of the capture system for sure. And on the rendering side, so for instance, we take here, we have a texture file, we have a texture stream, a geometry stream, and when we reconstruct, we are able to reconstruct the different views, and it's on a video. And again, the reconstruction, the virtual view is created on the device. So this MPEG efficient solution that is provided by MPEG contributors to the industry is really important because it really makes its fundamental streaming take the leverage of the video codecs like HEVC or VVC, so that really you have efficient compression schemes. So whatever the input stream is, point cloud, multi-view, multi-plane images, then you make this packing, the 3D processing, and you create video streams, 2-3 video streams. And on the decoder side, you just decode those streams and reconstruct. So it's agnostic to video codec. It shares the same bit streams. It brings variable bit rates. It enables real video streamings, and it's based on lightweight video-based players. It's not a game engine rendering device that you have to have on your devices. It's really a video player. So here on booth 103, during this event, we are presenting with Interdigital and Philips, we are presenting the implementation of video-based immersive codecs, these V3C codecs, in use cases like telelearning. We start with this telelearning with pre-recorded content that you can access. So for that, you will have access to an application. So this application, we want you to enjoy any type of content. You enter the content, you start discovering it with a 2D video, as you would have done today. And then you want to engage further. And for that, you go with MPEG Immersive Video to get part of the scene and get more information, get more immersed. And then you want to get further. And for that, you go with point cloud compression so that you can just look around the character. So you are able to come and view the different content with different topics. So we could have done physiotherapy, but we wanted to be more on hobbies and passions. So that's why we propose soccer, we propose dance, or some kind of more artistic creativity with the a kind of cinema school that creates cinema content. So really, you can come and enjoy that on different devices. So the platforms that we are showcasing, we have some pre-recorded content which has been recorded with different type of rigs. And then we stream that with the V3C system standards. And then you can access to different type of devices. And that's what we show also, is that immersive content on a 2D screen already brings you immersiveness, already brings you more engagement. You have that on a Windows platform, on an Android platform, but you also have that on a smartphone. You have the smartphone and you are able to render and play this volumetric video on a smartphone. Or you can use headsets so that you can go also with AR applications. Finally, if we want to go one step further, here the first part is really about the video asset itself and how we deliver that. But then we were talking about more going into a larger scene, a full Copresence environment. So for that, you will need to have some tools for scene compositing, for scene descriptions, and having also the way to make synchronization between the media and all these elements of your 3D environment. And for that, we are showcasing also some extensions of scene descriptions APIs so that you are able to address multi-users applications and collaboration, you see, if we go with the telelearning approach. That's all for today. Thank you.
Thank you so much for that amazing talk. Now, do we have some questions? Comments? Yes. Thank you.
Thank you very much for the presentation. So right now this is in prototype, right? When do you expect for it to be used and start being used?
Yeah, so yes, we are showcasing the implementation as prototype, as you say, but it's real implementation. The standards is ready, okay? So it has been released. So we have the standards implementation. So this is up to now to the ecosystem to take that, to leverage that. So we work really with the ecosystem on the creation side to have creators. We work on the booth with some creators. We have, for instance, XD Productions who have provided the content. So they are service providers. They are provided the point cloud. So now we work with them to show how this type of content can be streamed. And then the implementation, you have a reference implementation. So you can implement that on a plugin, on a Unity base. We have a Unity application. You have a plugin, specific plugin to render this type of content. So it has been released, let's say, last year for point clouds and also MIV. So now the standard is here. And the goal for us, for InterDigital and Philips, is really to enable the ecosystem, to bring that to the different players, platforms, telelearning platforms, for instance, where they already manipulate such content, so that you can bring additional with this type of content.
Great. Thank you.
Thank you.
We have a question over here. I'm just going to give you the microphone. There you go.
So what's the bandwidth in terms of the amount of data that you need? Like if you really want, if you want, at the end when you render, you need real time, because self-induced parallax means that if you move your head in front of your display, you want immediate response, right?
Yeah.
So
we have two things. When you talk about the immediate response about you moving your head, what is important is that we are not streaming 2D content. We are not rendering this virtual view on the cloud and viewing on the device. It's the device itself. On each frame, what we call the frame, you have the full information.
Sure.
So the position, the reactivity to the position is made on the device. So here we reach you are on the VR headset, all the frame rates of the VR headset. It's really rendered and it's really more than real time on the device.
Yeah,
then there is the other point about the bandwidth. So that was the second. And the bandwidth, yes, it depends also on the amount of information that you stream. So we can go to few megabits per second for a single character on the point cloud to 20, 30 megabits when it's the full scene, or much more, 50, 80 megabits if you capture with lots of cameras. Today, we consider, and what we implement is about a factor of 300 between the source data and the bit rates of what you transmit. But then what is important is that you transmit the volume, the full information, and then, yes, the adaptation to your position is done on the rendering side.
Yeah, no, I understand like that. Like if you're in a dead environment, then you need only that one frame, and the rest is done on the rendering end. But the environment itself might be alive as well. So there might be another person in there, or moving animals, or like if there's motion in the environment, then you need the volumetric encoding 60 times per second.
Yeah, when you are, yes, in the other sides, yes, when you have, again, yes, the real-time encoding, that's really, yes, that will be the more challenging, as you're right, when we will go to Copresence, when you have also, I have also in real time to send my content. So that's, you will have to have enough means to encode locally and then send. That's really, yes, one of the challenges that we have seen just with the talk before, is that when you go to this Copresence, you may not have the, you will have a limited capacity of capture because we will not have high-end rigs, but we will, you will have perhaps less immersiveness, you will have less details, but you will be able, with a few type of cameras, will be able to make that. And it's really one of the challenges and one of the area of where we are working on is on this real-time encoding, yes, and delivery on upload, in fact, bandwidth, which is important. In the use case, that's why on the roadmap I proposed, we start with Telelearning, where we push this volumetric content and let the user engage with this content. And we are working still on the parts that it will be dual link. That's right.
Great. And do we have any other questions? Comments? No? Final thoughts about this exciting new area? Nothing? All righty. Well, thank you so much. Let's give another hand to Valerie.
Thank you.
Thank you very much.